Okay, so let's do problem number 3 from worksheet number 3 on constant acceleration. But first,
all right.
Yeah. Yeah. I apologize. All right. Okay. Yeah, that was awkward. All right, so number 3, it says, a stunt driver testing the use of airbags drives a car at a constant speed of 25 meters per second for a total of 100 meters. He applies his brake and accelerates uniformly to a stop just as he reaches a wall 50 meters away. So we want to sketch a qualitative position versus time and velocity versus time graph. How long does it take for the car to travel the first 100 meters? And remember that the area under velocity versus time graph equals the displacement of the car. How long must the brakes be applied for the car to come to a stop in 50 meters? So we're looking for time there. And now that you know the total time traveled, sketch a quantitative velocity versus time graph. And what acceleration is provided by the brakes? How do you know?
Are you okay?
Evidently not. All right. I don't know if I'll keep this V naught. All right. So, I'm going to do this problem differently. So we've got, given. So I got a car on a road, stunt car, whatever, and driving 25 meters per second. And at first it says that it's a constant speed. So that's A equals 0, right? Another way of saying constant speed, you can put V equals a constant, or you can say A equals 0. Until you go how far? 100 meters. And then what happens? Here's our same car. We'll say this is V naught equals 25 meters per second. But now we have an acceleration, and we slow to a stop in 50 meters. So when we reach 50 meters, V equals 0. And we have a constant. This is a constant. And given, now let's just do A. It says sketch a qualitative position versus time and velocity versus time graph. So qualitative. So here's position versus time. Now let's say we start at the origin. They don't really tell us where to start. We'll start at the origin. And we're going constant velocity, which means this is a straight line, like this. And then what happens? Then we slow to a stop. You know what? I should make that steeper. How much time do we have? Not much. So, and then we slow to a stop. Now this is qualitative, so I don't know if the times, but how do I know that it stopped? It's got 0 slope right here. So it's got positive constant slope, and then it stops. And now the velocity versus time graph for this. Oops, I didn't need to put that negative part there because it's all positive velocity. We have positive velocity, and then it goes to 0. And I think that's all it asked me to do. Position and velocity versus time graph. So for part B, how long does it take for the car to travel the first 100 meters? Well, it was going 25 meters, so delta x will be equal to the velocity, 25 meters per second, times time, right? But I know this is 100 meters per second equals 25 meters per second times time. Divide both sides by 25. And you get, should not be meters per second, I'm sorry. I'm trying to go too fast and I'm making mistakes. So what is 100 divided by 25? 4 seconds. So now I know that this is going to be 4 seconds right here, where this change happens. Now part C, it says, remember the area underneath the velocity versus time graph equals the displacement of the car. How long must the brakes be applied to come to a stop in 50 meters? So what we're saying here is that this area of this triangle, 1/2 the base times the height, has to equal 50 meters. Well, what's 1/2? What is the base? The base of this is the time that we're braking. What is the height of this? Well, my initial velocity. And that has to be equal to 50. So T is going to be equal to, well, divide both sides by 25, and you get 2. Multiply both sides by 2, and you get 4 seconds. So it's the same amount of time. So from here to here is 4 seconds, so this is actually at 8 seconds. So there you go. Does everybody see how to do that? Does that make sense, Ronnie? Because you asked about this, and I'm going really fast. Okay. And then part D. Now you know the total time of travel. Sketch a quantitative velocity versus time graph. Well, okay. So 5, 10, 15, 20, 25. Velocity meters per second. 1, 2, 3, 4, 5, 6, 7, 8. Time in seconds. Looks like that. And then part E, it says, what acceleration is provided by the brakes? How do you know? Well, acceleration is the slope of this line, which is delta V over delta T. Well, the final velocity is 0 minus the initial velocity is 25 meters per second divided by a delta T of 4 seconds. It took 4 seconds to brake, yes? So A is going to be equal to negative 25 divided by 4. That's going to be negative 6.25 meters per second squared. And that's my answer for that. So that's a very, very fast number 3. I guess we have more time than I thought. I was thinking 12:01, but it's 12:05 today. So, but you can see how powerful these ideas are. I mean, you can figure out exactly what your acceleration has to be. What, if you're doing a stunt, if you're doing a movie and your car's going to be driving around, you can figure it out exactly what you have to do. Any questions on number 3, worksheet 3? That is all.